So today we're going to talk about related rates, and I'm going to do a few examples of related rates for you to help illustrate the thinking behind each one of these problems. The first thing you want to be careful with related rates is a lot of students tend to memorize problems in calc, and this is not the case with these problems, especially with these problems. It shouldn't be the case with anything in calc, but especially with these problems, you don't want to memorize because each problem here, I can ask it a variety of different ways, and I can use the same equation, the same numbers, and ask you multiple different ways. And so what students end up finding is that if you memorize the problem a certain way on an exam or an assessment, you get the problem a different way, and now you're stuck and you don't know how to approach the problem. So you really want to understand how these problems work in order to be successful on the exam with these kinds of problems. And so I've developed this problem solving strategy for you for these related rates problems, and there are 5 steps in order to help your mind get set into how to answer these questions. So make sure we're not memorizing these problems and we're reading the problems very carefully as problem to problem differs, although a lot of them might seem like they're the same type of problem. Read it carefully to really know what the problem is asking of you. So the first thing you want to do when you get a related rates problem is you want to introduce the notation for all the quantities that are functions of time, meaning things like volume and area and radius in these types of problems are going to change with respect to time. That's what makes them rates. If something is changing with respect to time, that's not only going to have a constant value, but it's also going to have the derivative or the rate at which it's changing at a certain time. So we want to introduce and we want to acknowledge the things in these problems that are changing with respect to time. And if possible, you always want to draw out a diagram to show these quantities. A diagram really helps you understand what is going on in the problem. And you'll see as we do some of these examples in class and on here. The second thing you want to do is identify the information given, and you want to identify what the unknown rate is in terms of derivatives and in terms of notation that's specific to you and how you're going to answer the problem. So usually I typically stick with like the radius. I'll use r to represent radius or r prime to represent the rate of the radius, but it's totally up to you. I would just stick with the basics, radius for r, area for a, and stuff like that. But it's totally up to you. You just have to define what your problem is asking of you. The next thing you want to do is we're going to relate the quantities of the problem using well-known mathematic formulas. A lot of times these problems, in order to answer them, you have to come up with a relationship between your unknown value and the values that are given. And to do that, you're going to either use the Pythagorean theorem, similar triangles, trig identities, geometric formulas for volume and area, and all that stuff. So they should be equations from algebra, from your past math classes that help you relate the unknowns to the known values in the problem. So sometimes you're going to have to use geometry as well to eliminate one of the variables by substitution. That happens when a problem arises where I take the derivative and now I'm stuck with a variable that I have no information about in the problem. So now I'm solving for my unknown variable and another variable that I have no information about. In this context, we're going to have to eliminate that one variable, so we're just solving for one variable. Key thing here is that we're just going to be solving for one variable. After that, we're going to use the chain rule. And why are we using the chain rule? Because all the quantities are functions of time. And we know from the chain rule, whenever I'm taking the derivative of a function, whether it be with respect to x or whether it be with respect to y, I'm going to get a rate associated with it or a chain associated with that derivative. After you use the chain rule, along with other derivative formulas, we're going to solve for the unknown rate by substituting the given information that was given. So that's where we're heading with these problems. These 5 steps should help you ensure that you're doing things right in these problems, and so we can dive right into the first problem here. It says air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. Typically the way I want to set these problems up is that I want to write down my givens first. I also want to write down any equations that I'll be using and draw the image if it's applicable. And then I want to solve the problem. And this is how I set up most of my related rates problems. Just to keep everything organized and in order, I set everything up with the givens, equation, and then the solution, just so everything flows together. The next step here is I'm going to be looking at the problem and asking myself what's being given. So air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. When I get to this 5, I have to ask myself, is that a constant value or is that a rate? And that's very essential in these types of problems. And so here it tells you that this is a rate. The air is being pumped into the balloon at a rate of 5 centimeters cubed per minute. And so that's going to be one of my rates. Which one is it going to be specifically? Well, if you look at the units, first of all, I'm pumping air into a spherical balloon, which is a 3D object, and the units are cubic centimeters, so that's going to be volume, and when I have it per minute, that's going to be a rate. So what is that going to be? The rate of a volume. So this is going to be signified as dV dt, or v prime of t. This is going to be equal to 5 centimeters cubed per minute. I keep reading. I want to determine the rate at which the radius of the balloon is increasing. I want the rate of the radius. So I'm going to write that as dr dt, or r prime of t, to signify the radius, and I don't know that value. But I know that I want it. It's going to be increasing when the diameter is 20 centimeters. So I've written down all my givens. Next I come here to the equation / image. In this case, the image is not really necessary. It's a balloon. We're pumping air into a balloon. The image is not going to really help us any way in this circumstance. So I need an equation that associates volume and radius, and that's going to actually be the volume of a sphere. So the volume of a sphere is given by the equation v of t is equal to 4/3 pi r of t all cubed. And typically these volume equations will be given on the exam. What's not going to be given on the exam is things like the Pythagorean theorem, similar triangles, the law of like the trig functions, like the law of cosines, the law of sines. You should know those. But these complicated volume equations, like the volume of a sphere, the volume of a cone, stuff like that, would be given on the exam. So you can take this equation as given. So now I'm going to look at this problem, and I'm going to say when I take the derivative in terms of time, I'm obviously going to get a chain rule for all this volume and this radius. Do I have all the information necessary to answer this question? So let's take a look. I come here to my solutions, and I have my equation, volume is equal to 4/3 pi r cubed. I just dropped the r of t here. We know it's in terms of time, but I just dropped it for the sake of it looking better when I'm doing the derivative. Taking the derivative, what's the derivative of v of t? Well, this is just 1 times the chain dv dt, or v prime, is equal to 4/3 pi is a constant. We're going to take the derivative of r cubed with respect to time. That's going to bring down the 3, keep this function the same, decrease the power by 1, and keep the chain, which is r prime, or dr dt. So now that I've taken this derivative, I have a variable dv dt, which is given. I have it over here, it's 5. I have this constant, that's no problem. I have dr dt, which is what I'm solving for. But do I have r? I have to make sure that I'm only solving for one variable. Do I have r? I don't have r, but I have diameter. And we know how to solve for radius. If given diameter, the diameter is equal to, or the diameter over 2 is equal to the radius. So in this case, it's 20 over 2. So the radius is 10 centimeters. And now I have all the information to answer my problem, so I go ahead and just plug in the numbers. The volume is 5, the rate of the volume, is equal to, we can cancel these 3's out, which leaves 4 pi. R squared I just solved for, this would be 10 squared, and dr dt is what I'm solving for. And go ahead and solve for dr dt. Here I have 5, here I have 4 pi times 10 squared is 100. So I'm going to have 400 pi on this side. How do I move it to the other side? I'll divide by 400 pi. And dr dt is going to be equal to 5 over 400 pi. And a lot of times we are asked if we wanted to simplify or not. In this case, you can simplify, you cannot simplify, it's up to you. What's important here though is that you put your units. So if you were to simplify, this would be 1 over 80 pi. And my units, this is radius, remember, but it's radius within a rate. So I'm going to have a rate as a unit. My distance units are centimeters. My rate is minutes. So your answer is going to be 5 over 400 pi or 1 over 80 pi centimeters per minute. And that would solve the related rate problem for you in this circumstance. All right, so let's move on to the next one we're going to do. It says a tank of water in the shape of a cone is leaking water at a constant rate of 2 feet cubed per hour. The base radius of the tank is 5 feet and the height of the tank is 14 feet. At what rate is the depth of the water in the tank changing when the depth of the water is 6 feet? And letter B, at what rate is the radius of the top of the water in the tank changing when the depth of the water is 6 feet? So again, we're going to start with our givens. We're going to have an image / equation. And we're going to have our solution. So in this case, maybe it would be better to draw the image first to see what's going on. So I have a tank of water in the shape of a cone. So I'm going to draw the tank of water in the shape of a cone. And we'll get to these numbers in a sec, but the base radius of the tank is 5 feet. The base radius of the tank is 5 feet. You have to ask yourself, is that a constant or is that a rate? Well, the tank is not going to be changing in size, so that 5 feet is going to be a constant number. So the base radius of the tank is 5. And the height of the tank is 14. That also is not going to change because the shape of the tank is not going to change. And we have some water in this tank. And so the water, however, is going to change. So the water is going to have a radius, we're just going to call it R, and it's going to have a height as well. We're going to call it H. Why am I calling it R and H? Well, because the water at this level is different in radius and in height than it is at this level, and it's different in radius and height than it is on this level. So these two terms are associated with a rate because the radius is going to decrease as we get less and less water, and the height is also going to decrease as we have less and less water in the tank. So the tank of the water in the shape of a cone is leaking water. Now we can write down our givens. So we have the radius of the tank is 5. The height of the tank is 14. The radius of the water is R. The height of the water is H. Now we're told that it's leaking water at a constant rate of 2 feet cubed per hour. That's a volume. It's a rate of a volume, so we're going to write V prime. And that's equal to, well, you have to ask yourself, is it positive or negative? And how do I answer that question? It's, well, is it decreasing in size or is it increasing in size? And so if it's leaking water, I'm having less and less and less water, that's going to be negative. So we're going to signify that with a -2 here. And they want to know at what rate the depth of the water in the tank is changing. So the depth of the water is associated with H prime equals, we don't know, when H is equal to 6. So we want to know H prime when the depth of the water is equal to 6. Now we need an equation that relates all these terms together. And again, this equation would be given on the exam for you. And it's the volume of a cone. And so the volume of a cone, we can write it here first. The volume is equal to 1/3 pi r squared times the height. So now looking at this equation, if I take the derivative of this equation, I'm going to have v prime, which I have. I'm going to have a product rule here between r and h, which would leave me with r prime, h, and h prime. But if I look back at my problem, and these of course are the radius and the height of the water in the tank, not the tank itself, because remember those we said are constant numbers, those aren't changing. So if we look back here, we're not given any information on r. So we have to eliminate this variable. We only want h. We're solving for h prime, so we need that in our problem. We have what the height is of the water. It's 6. We don't have r and we don't have r prime in terms of the water. So we have to eliminate this variable. And in order to do that, we're going to look at this image and say, well, these look similar to me. We have the relationship between the tank, which is a cone, and the water in the tank, which is also a cone. So the relationship is the radius of the tank, which is 5, corresponding to the radius of the water, which is just r, is equal to the height of the tank, which is 14, over the height of the water, which is just h. And we're going to solve for the variable I want to eliminate. And that variable is going to be r. I want to eliminate r. So in order to do that, I'm going to cross multiply. So I have 14r is equal to 5h. Solving for r, you divide by 14. r is equal to 5 over 14h. So now with my solution here, I have the equation volume is equal to 1/3 pi. Wherever there's an r, I'm going to replace with 5 over 14h. So r squared is 5 over 14h squared now, times h. If you don't see what I just did here, take the derivative of this equation right here. When you take the derivative, you're going to realize that you got stuck with a bunch of variables you don't have any information for in your problem. So it's not a problem if you take the derivative and you realize, well, I ended up with two variables I know nothing about. In that case, you know that you have to eliminate them, and that's why I did the relationship here. This is by algebra. So if you don't see it yet, take the derivative of this equation right here and then see if you can answer it by taking the derivative without eliminating. And you'll find that you can't because you're not given any information on r, or the radius of the water. So then you'll have to eliminate r, which we did here. Now if I take the derivative, well, let me clean this up a little bit first. We have volume is equal to 1/3 pi. This simplifies to 25 over 588. So the 5 times the 1 with the 14 times the 3 squared is going to simplify to, if I rewrite this, so 5 squared over 14 squared times this 1/3 will simplify to 25 over 588 pi h cubed. Now taking the derivative, there's no more product rule because I only have one variable. Taking the derivative, I'm left with v prime is equal to 25 over 588 is just a constant. And take the derivative of h cubed, it's 3h squared, h prime. Now plug in all the information we know. We know that volume prime is -2. This is going to be equal to 25 over 588 pi. 3 times, we know the height is 6. This is the height of the water, squared, and we're solving for h prime. So simplifying here, -2 is equal to 25 over 588 pi times 36 times 3, don't forget that, and times the h prime. And you can go ahead and solve for h prime, and when you do that, you should get an answer of -98 over 225 pi. And the units, of course, don't forget them. Height is in feet. This is feet per hour. Again, I don't want to do all the work for you, so make sure you know how to solve for h prime here by multiplying the 36 by the 3, multiplying that by the 25 over the 588, and then dividing everything out over this -2 to solve for h prime. So that's what the question was asking for in part A. We wanted to know at what rate the depth of the water is changing, so the depth of the water's rate is h prime, and that's your answer. Does this make sense in terms of a negative or a positive? Well, yes, it makes sense because the depth of the water is decreasing, right? Because the tank is leaking water. So the height of the water must be decreasing as well. Since the tank is leaking, this should be a negative, which it is. So we did something right. In letter B, I'm asked, at what rate is the radius of the top of the water in the tank changing when the depth of the water is 6 feet? Well, now they want to know the r prime. R prime when h is 6, which is the radius or the rate of the radius when the height is 6. So how do I do that? Well, I can go back all the way up here to my original equation, and remember, I don't have any information about the radius itself, so I can't use this equation, because if I do, I'm going to end up with r, and I don't know any information about r. But I have this relationship that I came up with. R is equal to 5 over 14h. And so I can use that and take the derivative of that. So if you take this, which is a true relationship because there's an equal sign and we made it true, because it's a true relationship from the cone. If you take the derivative here, you have r prime is equal to 5 over 14 h prime, right? Because the derivative of h is just 1 times h prime, the derivative of r is just 1 times r prime. Well, we have what h prime is, so if you take h prime and multiply it by 5 over 14, you should have r prime. And in this case, if you do the math, the r prime is -7 over 45 pi, and that is also in feet per hour. Again, you want to make sure that you can multiply this -98 over 225 pi by 5 times 14 to get your r prime answer in this case. This is from algebra, has nothing to do with calc, so I'll leave it up to you to do the math and work it out. So this is what r prime is, and you have to ask yourself again, should it be negative? Well, yes, because if the height is decreasing, then the radius, as it goes down into the cone, like it goes and it's leaking out of the cone, the radius is getting smaller and smaller and smaller. So the r prime should be negative, the h prime should be negative, so these both make sense as my answers. And so that's it for related rates, these two problems. We're going to do more on Wednesday. Remember this original page that we have here. Remember the 5 steps. Like I said, each problem is different, so you want to really pay attention to what the problem is asking for, and you want to pay attention to when I can eliminate a variable and when I shouldn't eliminate a variable, and you always want to make sure you're solving for only one variable. So if you have too many blanks, then you must eliminate one of those variables. Again, don't memorize these problems. Read the problem carefully and follow these 5 steps and these 2 examples to ensure success on these problems. And if you have any questions, feel free to email me. I am more than happy to answer any of your questions. And again, we'll do more of these examples on Wednesday, and the answers to the other 8 problems are posted on eSpace. So check those out and let me know if you have any questions. This is Ahmad signing off for now.